Right, so next is section 5.4. So everything we've done up until now has led us to being able to diagonalize a matrix. So can we use this diagonalization principle to our benefit? So the answer is, well, we can actually, one of the uses of diagonalization is to solve a certain class of partial differential equations. And that is what we're going to do in section 5.4. So first of all, remember that a differential equation is an equation involving unknown functions and their derivatives, right? And remember, the order of a differential equation is the order of the highest derivative that it contains. Now, again, the simplest differential equations are the first order equations of the form the derivative of y is equal to a constant times the function y. And remember now, in this case, y is a function of x, and so on both sides you've got functions of x, and y prime stands for the derivative or the change of y over the change of x. All right. Okay, now if we look at this this differential equation, y prime equals 4y, the solution to that equation will be all functions of the form y equals c e 4x, right? And you can easily verify that the left-hand side is equal to the right-hand side, where c is just an arbitrary constant. Now, very often we need initial condition to solve this constant c, and depending on what that initial condition is, that will influence the value of c. So for the initial condition where y in the point 0 needs to satisfy, needs to equal 3, we can easily solve for c, and c needs to then be equal to 3. Alright, so that's called, that condition, recall that that's called the initial condition. Okay, I'm sure you've all seen this before. And the problem of solving a differential equation subject to an initial condition, that is called the initial value problem. So we'll first find solutions, and then we'll make sure that it satisfies the initial conditions. Right, so let's move on to systems of differential equations. Now, this is where the diagonalization will become very useful, and its applications will become apparent. So let's say you've got a specific class of differential equations, and they are basically defined as follows. So you have this system of differential equations, right? And so basically, it is each derivative of each function is basically a sum between scalar multiples of various functions, where the functions go from y1 up until yn, and each one of these functions are, say, functions of x. Right, now we can write this system in matrix notation. We can write the left-hand side as a column vector, and again, what I forgot to mention is these aij's, they are all constants, right? And so we can write it as pretty much this n by n matrix multiplied by this column vector. Right, so in matrix notation, that just translates into that system there. Now the question is, where does diagonalization come into the picture? And we'll get to that just now. Right, so there, before we get to diagonalization, let's just get to just an example, right? So here they ask us, just go and write this system in matrix notation. Okay, so that basically, you can write that easily in matrix notation. So on the left-hand side, you've got your column vector. and on the right hand side you have you've got 2, 0, 0, you've got 0, 3, 0, and you've got 0, 0, minus 1. You've got y1, y2, y3. Okay, so that's your matrix, that's your system and matrix notation. There they ask us to solve the system. Okay, so your system can easily be solved where, of course, these are constants. Okay, and then the last one there, they ask us to just find, solve that initial value problem. Okay, so having solved that now, we can then easily solve for the constants C, D, and F respectively. So y1, what needs to happen there is y1 in the point 0 needs to be C e to the 0, which is C, and that needs to be 1. Okay, so basically C is equal to 1, so y1 needs to be that function there. Right, so the second one again, y2 in the point 0 needs to be that, and that is D, and that needs to be minus 1. So y2 then becomes minus e to the 3x. Right, so y3 in the point 0, again that needs to be f e to the 0, and that again needs to be 2. So that's going to imply that y3 is going to be 2 e to the minus x. Right. Okay, so that's straightforward. So now we know how to do the initial value problem, and now we can go on to discussing diagonalization. Okay, so now before I just want to mention something, and that is that if we look at this linear system, this system is was very easy to solve, and just note the following. Note that this is a diagonal matrix, right? And so if your system translates into a system where this matrix here, right, so this is this type of system here, if that is a diagonal matrix, right, then it's pretty much involves solving each one of these functions. Well, it's going to involve solving these functions, right, or these type of equations where I runs from 1 up until 3. And I mean, solving that directly is quite straightforward. The tricky thing comes in when you've got more, when you've got functions of that form, right? If you've got functions of or differential equations of that form, where you've got more than one term that you need to take into account. If you go back here, you see that we've only got one term to take into account, and then it's very easy to solve that directly. But what if you've got more terms, more than only one term on the right hand side? And it seems that when the system is when this matrix is diagonal matrix, then it circumvents the problem of having to deal with more than one term there, which is obviously more tricky. So that's where diagonalization is going to come in. So solution using diagonalization. So okay, so go back to if we go back to this system here. then we need to get rid of, we want that system of equations, we want it to be of the form where I don't have, for each variable here, the only thing I have on the right hand side is going to be a one function y1. The only function we have there on the right hand side is y2. And in general, the only function we have there on the right hand side is yn. That's what we want actually for it to be easy to solve. Okay, so go back, consider this system. Suppose it's not the case that you have that diagonal scenario, and it is actually more complicated to solve. And let's say that A is not diagonal, but I can diagonalize it. Right, so now what you do is you do a substitution, you introduce a new variable u. Okay, and then what you do is you write y as the matrix P times u. Okay, so we said you take y and you set y as P times u. And what do we have? We have that y prime is equal to, we said, A, that's my system. We've written it in terms of matrix notation. And we also know that A is can be diagonalized. So A can be diagonalized, and all right, so let P be the matrix that diagonalizes A. Okay. So then what you do is, as I said, so you replace y with a new variable. So there we replace y with the matrix P times the u. And u is, again, is a column vector of functions. Okay, so you're replacing the column vector of functions y with the matrix P times a column vector of new functions. And y is a function of x and u is still a function of x. Okay, so now from that, because these are all functions of x, you can take the derivative on the left hand side and you can take it on the right hand side as well. And then again from there, what you can do is you can do a substitution. Remember, we said y prime is a y. So basically, you can go and replace. You can replace y prime with that, and so you've got this thing that holds here. Okay. Then we know that y is pu, okay, from there. So, so we could take y, which is pu, and we're going to do the replacement. Okay, so there we've got our replacement. And then operating on both sides with P's inverse, because we know P's inverse exists, we get that system. And then from there, we can replace this matrix here with a D to indicate that it's going to be a diagonal matrix. Okay, now, so now we've got a new system of equations, and now what we can do is we can solve for u. and we can solve for U very easily. We can solve for U very easily because U is each row in the column vector of U prime. Let's look at the first row. It's going to look like this. It's going to be of the form constant times the first row entry of the column vector U. Okay, so I mean this system is a lot that's easy to solve, and you can do that for each entry in U prime. You can solve each entry individually. Now, once you've done that, once you've solved each function in the column vector U, you can then just plug it back in there and solve for Y by just multiplying the matrix P with the column vector U, and you can generate your whole column vector Y. So it's a very straightforward procedure. Okay, so that's what they've written there. So you do that, and then you do all your replacements as I described previously, and now you've got your new system. You've got this system here which you can easily solve directly, and then you can just plug everything back into that system there. Right, so basically in short, the procedure is quite it's quite brief. So what you do is you first make sure that A can be diagonalized, and then if it is, assuming that it is, you find the matrix P that diagonalizes A, and then you make the substitutions, right? You set Y as the matrix P times a new column vector of functions. You take the derivative on both sides. You do all of you then set U prime as D U, and we know D is this matrix here. Okay, and then you solve that system directly as we've described in the first example, because D is diagonal. And whatever you get there, whatever you solve the column vector U as, you plug it back in there and you solve for Y. So that procedure is better. It's better described with an actual example, which we'll do just now. Right. So in this example, we are asked to solve the system of differential equations. Right, so y1 prime is, we assume that y1 and y2 are both functions of x, and we are asked to solve the derivative of y1 equal to y1 plus 2 times y2, and the derivative of y2 needs to be twice y1 plus y2. Right, so the procedure as I described it is quite simple. So we do it as follows. Right, so there's my system of two differential equations, and we're going to just write this in matrix form. Right, so that's going to be my first vector. Right, there's my second column vector. Okay, and my matrix. Right, so this is that is my vector y prime. That's my matrix A. And that is my matrix or my column vector Y. Right, so let Y be P, where P is a 2 by 2 matrix, and this P needs to diagonalize my matrix A, and And this, of course, I can only define P if I know that I can diagonalize A, but we'll later establish that, in fact, A can be diagonalized. So we define Y as PU, where U is a new introduced vector defined by U1, U2. And U1 is a function of X, and U2 is a function of X. Now, taking the derivative on both sides, we get that y prime is pu prime. Okay. Right, so hence we take that expression. We know that y prime is it's that expression there. And we know that y is pu. Right, so we can replace y with pu. Right, and so applying on both sides with p's inverse, this is now assuming p exists and its inverse exists as well, which we will establish just now that it will in fact be the case. We can go and solve for the derivative of u in terms of the vector u, and P and A are both matrices. Now recall that the matrix A was this matrix 1, 2, 2, 1, and now what we're going to do is we're going to find the eigenvalues of A. Now to get the eigenvalues, we want to find the determinant of this matrix, and that is basically going to be the determinant of this matrix, which is going to be the matrix lambda minus 1, minus 2, minus 2, lambda minus 1. Right, and the determinant of that is going to be lambda minus 1 squared, right, minus 4. Okay, so the eigenvalues are where this is where the determinant is 0. Right, that is going to be the that's going to occur when lambda is 1 plus or minus 2, which then implies that lambda is either minus 1 or lambda can also take on the value 3. Okay, so those are the eigenvalues. Now what we do, we go and find a basis for the for each eigenspace. Right, so that matrix becomes 3i minus a, which is going to be the matrix. So that is going to be where lambda is 3. That's going to be 2 minus 2 minus 2, 2. And then we want to go and look at the null space of this matrix. In other words, we want to, in actual fact, determine, we know that by looking at the null space of this particular matrix, that is going to determine the basis for my eigenspace. Right, so taking that matrix there, and we look at the null space. Okay, we look at the null space, and basically that translates into solving the system 2a minus 2b equals to 0, and the system minus 2a plus 2b equals to 0. Let's parameterize the unknown b, we set it equals to t, then we can then solve for A as t. Alright, so the basis for eigenspace corresponding to lambda equals 3 is basically going to be it's going to be the set that contains the following vector 1, 1. Okay, next up is the eigenvalue lambda equals minus 1. Right, so there we've got the vector of the matrix, so that's going to be minus 2, minus 2, minus 2, minus 2. Look at the null space of that matrix. So you're going to take this system and you're going to solve, you're going to find a basis. Right. That's going to correspond to the system minus 2a minus 2b equals to 0. And it's right, so that's going to be your system. And so the basis corresponding to lambda equals minus 1 is going to be right. So we assign the parameter t to the variable b, and therefore we can solve for a as minus t. Okay, so the basis for the eigenspace corresponding to lambda equals minus 1 is going to be that vector there. Right, so how do we compose our P matrix? We take our two bases, and then what we do is we form our matrix P. But we can do it as follows. We take that column vector there, and we take that column vector there. Right, we put them like that, and that is our matrix P. Alright, and we also know that P's inverse is going to be, alright, so there's P's inverse. So now we can just quickly go and determine the matrix P inverse AP, and that we can go and quickly multiply that out, and that is going to give us minus 1, 0, 0, 3, which is the diagonal matrix. So it's pretty much A that is diagonalized. Okay, so recall that P inverse AP U is U prime. So, and we also said that P inverse AP is the diagonal vertex, is the diagonal matrix minus 1, 3. All right. So basically, our vector U prime then becomes, so it's basically this matrix here, okay, multiplied by the vector U. Right, there we go. Okay, right, so that implies basically that U1 prime, U2 prime is going to be equal to this whole matrix. And then if we multiply that out, we get we get basically that u1 prime is minus u1. That's my first one. Second one is we also have that u2 prime is 3u2. Right, so we can go and solve for u1 as a constant c multiplied by e minus x, and we can go and solve for u2 as a constant d multiplied by e3x. Now recall that we defined y as pu. So that is going to imply that y1, y2, we said, is going to be the matrix P multiplied by the vector u1, u2. Okay, and the matrix P is, right, we solved for P as that. Okay, so from there, it follows then that y1 is equal to minus u1 plus u2, right? And we solved for u1 as, right? And we solved u2 as then also we have that y2 is u1 plus u2. We solved u1 as, and we solved u2 as that. Okay. Right, now the second question. Okay, so here they ask us, find a solution of the system that satisfies these initial conditions. y1 in the point 0 needs to be 1, and y2 in the point 0 needs to be minus 1. Recall from the first question that we solved y1 and y2 as those two functions respectively, and the initial conditions we are given to solve are the condition where y1 in the point 0 is 1, and in that case we have that y1 in the point 0 is going to be minus c e in the point 0 plus d e3 in the point 0, which is going to be e0, and that is going to be minus c plus d has to be 1. The second initial condition is that y2 in the point 0 that needs to be minus 1. So again, that is going to be c e0 plus d. e0 again, which is going to be c plus d, and that needs to be minus 1. Okay, so taking the first one and adding it to the second one, that needs to be the same as 1 minus 1, which is 0, and therefore from there we get that 2d 0, which implies that d is 0. Now because d is 0, this is going to imply that minus c is equal to 1, and that is going to imply that c is equal to minus 1. For the original system to satisfy the initial conditions, we need these values to be satisfied, okay, which implies then that y1 is e to the minus x, and y2 needs to be minus e to the minus x. Alright, so that is a nice little application of diagonalization which enables us to solve this this type of differential equation. Okay, so it's got a nice, if you confront it with a system of differential equations of this particular form, then diagonalization can work quite nicely. Now, I mean, it can obviously be extended to other types of differential equations as well, but this is a specific application for this type of for this class of differential